All right, welcome back. I hope you had a nice vacation. We've got a homework assignment due on Thursday, and we're going to take a look at some of those problems at the end of class today. I already got a couple of emails, so I know that many of you spent your Thanksgiving holiday wisely, which is to say engaged in fluid mechanics homework. So good job on that. All right. Any schedule questions before we get into it? All right. Well, you haven't been thinking about this stuff for a little while, and so let's do a quick example just to warm up. This is an extension of some of the examples that we worked in class last time. We have two tanks that are connected by a pipeline that's physically sloped. Now, in future classes, we're going to talk a lot about slopes, and sometimes we'll talk about the slope of the pipe. Sometimes we're going to be talking about the slope of the energy grade line, which is something different. Here, this slope is referring to the physical slope of the pipe, meaning that as the water flows from west to east, it does that through a pipe slope of 3%. So there's 2 points of interest that are 545 meters apart, and we have measured the pressure difference between those 2 points. 86 kilopascals. Now, the pressure difference is going to be due to two factors. Now that we're talking about the energy equation, we don't have to ignore energy losses anymore. The effect of pipe friction reducing pressure. But pressure is also going to be different because of the elevation difference. And so, with the energy equation, we're going to try and resolve the mystery here and find out what's the head loss between the 2 points. And so if we look at the energy equation and the diagram that's provided, we can start on the left side of the equation, and of course we know that's the pressure head, the velocity head, and the elevation head. But then the unique term with the energy equation, first on the left side, is H sub P, which means pump head. And here, just from the diagram, it's clear that there's no pump between the 2 points of interest, between point 1 and point 2. And by the way, why did I select point 1 to be this location and point 2 to be the other one? Anyone remember why it matters and how we choose which is 1 and which is 2? Exactly right. So she said, wherever the water is flowing to is location 2. I guess that's a good way to remember it, right? But location 1 is upstream, location 2 is downstream. And the reason why of that is if you look at the energy equation, we've got certain things on the left and certain things on the right. And on the right side of the equation is going to be our head loss term, which means that however much energy is left at 2 is going to be reduced by the amount of energy that was lost due to head loss. And so that's on the right side of the equation. So location 1 is upstream, location 2 is downstream. And here it says water's flowing from tank W to tank E. So any questions so far? Just trying to interpret the situation here. So P1 minus P2 is 86 kPa. That means that P1 is higher than P2. Now, if conditions were static, we would expect the reverse to be true. Because location 2 is lower. And so hydrostatic equation says that as you move through a fluid, that the pressure increases as you go down vertically. So here, P1 minus P2, that means that P1 is higher. And so what that tells us is, remember the two factors that are causing a pressure change. One is elevation difference. 2 is the energy loss. So the energy loss between 1 and 2 must be greater than whatever pressure is being picked up as you go down through the fluid. Now, the energy equation will resolve all of that in sort of one step. When we substitute everything in, we can find the head loss, H sub L. And so that's what I'd like you to do. We don't know the absolute pressure at 1 and 2. We only know the pressure difference. but that's good enough. We can rearrange the energy equation in terms of P1 minus P2. Now it says here that the fluid in question is water, so that defines the unit weight for us. We're going to assume that the conditions here are turbulent, and in fact we'll just use the alpha of 1, but it ends up not mattering because the diameter of the pipe isn't changing. And so whatever velocity that the water has at location 1, it has the same velocity at location 2. So you can cancel out the velocity head term, and whether we use 1.0 or 1.05 for alpha ends up not mattering. All right, so I'm going to pause the recording. I'd like you to try and calculate H sub L, the head loss between the 2 points that's caused by friction. Let me just mention one more thing. You'll notice the distance 545 meters. That's the horizontal distance between the 2 points. And 3% is the slope, meaning that for every 100 feet or 100 meters of horizontal, there are 3 units of vertical change. Okay, so just in a similar way that we don't know the actual pressures at 1 and 2, we only know a differential pressure. So similar to that, we don't know the actual elevations at 1 and 2. We can find a differential elevation, though, using the slope. And so the way I handled that is just saying, let's say that the elevation at 2 is 0, picking an elevation datum. And so that means that Z1 will have to be some elevation above it. So every 100 meters of pipe length, horizontal, is going to add 3 meters of elevation. So since there's 545 meters of horizontal pipe length, that means that Z1 is 16.35 meters above it. Now we already talked over the bit about the velocities being the same. There's no pump, no turbine. So both of those terms are going to cancel out. Rearranging energy equation to solve for head loss, it's just going to be the pressure difference divided by the unit weight and the elevation difference. So we're losing 25.12 meters of head as the water flows between those 2 points. Now, I mean, the implications of that, there's a lot we can do with that information. What it means, for one thing, is that we go back over here, the head loss that we've the pressure difference that we've measured, we can use the head loss that we've calculated to identify the elevation difference that there has to be between pipe W, tank W and tank E. If we want to achieve a certain flow rate, then the driving force, as we talked about last time in class, is the elevation difference between the 2 tanks. And if we don't have the elevation difference that we need, we can select a pump to add additional head. You can calculate, there are these curves that manufacturers will provide. You can calculate the amount of pump head that's being added for certain flow rates. And so we know from this example we've just calculated that between the 2 points there's 25 meters of energy loss. That energy is just, it's gone. It went into the pipe interaction with the water. It's due to pipe friction. And so it has to come from somewhere. It either has to come from an elevation difference or it has to come from us adding the pump head with the pump. So we're going to talk a lot more about pumps in future classes and next semester in 331. But that sort of refreshes our memory on the energy equation. Any questions before we move on? Any questions from the example? Everybody seemed to be getting 25.12. All right, well, let's review a little bit of terminology. This is a slide that we didn't get to last time. And so energy, as we've been using it, the energy equation is having units of meters of fluid. And you can see each one of the terms of the energy equation The hint here is that elevation has units of meters, but each of these terms is dimensionally consistent with units of meters. And we can also measure energy in joules. And the term energy and work are in some ways interchangeable because we use energy to do work. We talked about shaft work in class previously, where the work that's done to a system by a pump, or the work that a system does to a moving generator, can be measured in terms of joules. And the other term that we're going to start using today is power. And the difference between energy and power is that there's a time unit in play when we're talking about power. And because watts are joules per second, the power equation that we're going to use most often will incorporate the flow rate, which is a volume of fluid per time. So cubic meters per second multiplied by the unit weight of some fluid multiplied by the pump head or the turbine head. This equation is a little bit interchangeable. We can use it to calculate how much electricity is consumed by a pump that's lifting water, or how much electricity is generated by a turbine that's producing electricity by taking pressure out of a pipe system. And so, of course, there's efficiencies that also have to be accounted for, and we'll look at that today. But here's the power equation, and it gives us units of watts when you multiply cubic meters per second of flow rate by newtons per meter cubed, which is our unit weight, and meters of head. It turns out to be watts. All right, so what we're going to do, just to sort of break things up a little bit, is I've got a critical thinking activity that I'd like to distribute here. And I'd like you not to consult your notes as you work on this. I ask you to, as the first thing, write the energy equation from memory. So don't look before you set your notes aside. See if you can write the energy equation from memory, and then explain why there are differences on the left side of the equation versus the right side of the equation for energy. And then there are a few other questions after that related to the figure that's on the page. And so there's a front and a back of this. I'll give you a few minutes to discuss it. It's okay. You don't have to do it individually. It's okay to discuss with your classmates, but don't consult your notes quite yet. Did everybody get a copy? Well, let's talk about some of this so far. So hopefully when you wrote the energy equation from memory, you were able to get at least some of the high points on there. A couple of things I'll point out. One is that the alpha is actually different at 1 than 2. It's not necessarily the same alpha. You know, if we're being maximally precise, the alpha is going to depend on the flow conditions at 1 compared to 2. And so it's feasible that if you had a pipe diameter change, that you could have laminar conditions at one location and turbulent at another. And so I wanted to first just point out that alpha 1 and alpha 2 are different. Now, the differences between what's on the left side and what's on the right side of the equation. Now, the way I put it, there's lots of ways to explain it, so you don't have to change what you've written, but let's just kind of point out that on the left side is the pump head term. And why is it on the left instead of being on the right? Well, the thing we have to remember is the standard notation is that we say water flows from 1 towards 2. And the energy equation is saying the amount of energy at 1 is equal to the amount of energy at 2. You know, the two energies are equal, except for some differences along the way. And so on the left side, we put the pump head term because that adds energy. And so it says that the amount of energy that was originally at 1 plus whatever pump energy is added is equal to how much energy there is at 2 minus, you know, there's also the energy that has to be accounted for, the turbine head and the head loss. Both of those are going to reduce the amount of energy that's available at 2, and so that's why we put it on the right side of the equation. Is, you know, this energy equation is basically an accounting. So I hope that you found some way to explain those same ideas. There are a couple other questions on your handout. I want to make sure that you have enough time to consider them. So on the back side of the paper, we'll take a couple more minutes for you to think about what is the meaning of the R to D on the figure there. So here's our figure. Is it a turbine or a pump? What is the meaning of R to D? And then besides the elbow, what are some other local energy losses that could occur? And then finally, what are factors that cause friction losses? All right. Hi. A fitting is something like this. It's like where some change is happening in just a single spot. Yeah, that's a fitting. If you've got really good vision, you can see how I put it. Okay, that symbol. It's kind of that symbol is used interchangeably for both pumps and turbines, and sometimes to know which it is, you have to interpret the context. And it's a pump. And the way we know it's a pump is that the flow arrow shows that the water's going from the tank on the left to the tank on the right. But the tank on the right has a higher elevation, and so we have to have a pump to lift the water and overcome the friction losses that exist there. So it couldn't be a turbine. There's no energy to extract from the system in that case. Now, if the water was flowing the other direction, it could be either. We wouldn't necessarily be certain what it would be. Because potentially it could be a turbine if water was going from the right towards the left, because there is an elevation difference there of 30 meters. But it could also be a pump if water is just flowing by gravity, maybe it's not going fast enough. And so you'd have to add a pump there to speed up the rate of flow. because remember that the rate of flow is governed by the friction losses encountered by the water as it flows through the pipe. Now, there's going to be pipe friction there that's limiting how much flow goes between the tanks. So as pictured, it's definitely a pump. If the water was going the other direction, we wouldn't be so sure. Any questions about that first bullet point? How many of you got the R to D figured out correctly? You managed radius to diameter. So I'm curious to know, in your own words, how did you put why it might matter? Why do you think it's given? What did you write on the page there? Anyone willing to share? Yeah, go ahead. Perfect.
The sharp change will change, like, where roughly so there'll be more of a loss than it just, like, slightly changing.
Very good. Yeah, and we've seen that in the lab on the pipe rack. There are a couple of fittings, as they're called, on the pipe rack in the lab where there's a 90-degree, like, instantaneous, sharp-edged elbow, and then there are more gradual transitions. And if you plug in the pressure meter at those 2 points, you'll notice that there's more pressure loss at the immediate 90-degree elbow with no gradual transition. And so in a future class, we're going to have pictures like this where we're going to have to count up the number of fittings there are and find out how gradual transitions will be, and then go to a table and figure out how much energy is lost at each one of those fittings as a function of how much turbulence is induced by the fitting. All right, great. Other spots besides the elbow. Now, the pump that's here, it's definitely some place where the flow is undergoing a big transition, but we don't consider any local losses that might occur at a pump. We kind of build that into our calculation or estimation of how much head the pump itself is adding. And so the only two other spots where something different is happening is at the inlet and at the outlet. And that same table that we use in a future class to do the accounting of how much energy loss is there from place to place, that same table will tell us that in an inlet like this, typically you'd lose half of your velocity head as a local loss at an inlet, and in an outlet you'd lose all of the velocity head as a local loss. And so at many of these isolated locations, how much energy is lost is dependent on the velocity of flow at that location. So that's a preview of what follows. And then the last thing, besides the fittings, there's also friction losses. And the three factors that would influence friction loss here, the quantity of friction losses, number one, what the pipe is made out of, because if it's a nice smooth plastic pipe that has low roughness, it'll extract less energy from the system than if it's a rough pipe, like maybe ductile iron or even like a corrugated steel. Those would both take a lot more energy out of the system than a smooth plastic pipe. And then velocity of flow and diameter of the pipe are kind of interrelated. And if you have a bigger diameter pipe, that will reduce the velocity of the flow for the same flow rate. But they're accounted for separately because those two variables can change independently. You know, if you have a certain diameter pipe, you can increase or decrease the flow rate through a system, and then that'll also have an effect on energy loss. All right. So hold on to this. We'll continue it with some additional related questions in the future. Now, let's look at another calculation example. Here we have an elevated reservoir on the left, and water is flowing from the elevated reservoir to a lower reservoir through a penstock, which is just another name for a pipe. And the penstock feeds into a turbine here, where electricity is being generated, and we're going to consider how much electricity can be generated and the effect that efficiency has. There's some information that we know about the system. There is an elevation on the upper reservoir on the left, elevation of the lower reservoir on the right. Head loss is just calculated for us. This head loss must have been estimated or determined based on the known friction characteristics of the penstock and looking at the velocity of the flow and so on. But that's already given, so we can substitute that directly into the energy equation. And then we also have the velocity of flow through the penstock. So the average velocity is 2.4 meters per second. Now here's the power equation that I showed you earlier. We're going to want to know, in this case, how much electricity can be generated. And the way that we'll do that is by putting in the flow rate, the unit weight of the fluid that's flowing, and then also the turbine head. Now the turbine head you can calculate from the energy equation, which we've seen a couple of times today. So you're going to have to rearrange the energy equation and find out how much head can be extracted by the turbine and then put it into the power equation. Now this, as you see it on the screen right now, assumes 100% efficiency. So what I mean by that is this turbine consists of two parts. It is a blade that is going to be turning the flowing fluid into like a rotating shaft, and then attached to that is a generator that is turning the movement of the shaft into electrical energy. And both of those are going to have losses. Neither one of those two components is 100% efficient at converting one form of energy into another. And so maybe a typical efficiency for a system like this could be 70% efficient. All right, so now look at the power equation. If we have a certain flow rate, which you can calculate from the continuity equation, you've already got the diameter and the flow velocity. So from those two things you can find Q. The gamma is this is water that's flowing. So you already know the gamma for that. Now, H sub t you'll calculate from the energy equation, but if we just substitute those three terms in, that's assuming 100% efficiency. So you'll get a certain number of watts from that. If it's 70% efficient, will you be getting more watts for the system or less? Less, right. And so the question that sometimes confuses students is like the 70%, or expressed as a decimal, 0.70. Should you multiply or divide this amount of watts by 0.7 to get the right answer when you've got 70% efficiency? Multiply, right, because we know, just sort of intuitively, that we can get less energy from the system if it's less than 100% efficient. Now, the opposite is true when you have a generator. When you've got a turbine that's creating electricity, then you would divide by the, for the pump, you would divide by the efficiency factor to find out how much energy is required, how much you have to put into the pump. So here we are generating electricity. 70% efficiency means that if it was fully 100% efficient, you'd get some amount, and then you multiply it by the efficiency factor to find out how much you actually extract, and the other 30% is just lost mostly to heat. But in the case of a pump, we'll do some pump efficiency calculations, then you would divide by the factor rather than multiply. All right, so now with that said, I'd like to give you some time to calculate how much electricity can be generated at 100% efficient and at 70% efficient. And the answer for both of those should be in watts. So it's really helpful to pick certain spots as location 1 and location 2 where you can cancel a lot of things out of the energy equation. And on the whiteboard here, I tried to guide you towards making that assumption that location 1 is at the water surface of the elevated reservoir and location 2 is at the water surface of the lower reservoir. And the advantage, of course, of doing that is that we know the elevation and the the pressure there. And we also know that in the reservoir itself, the velocity is 0. Now, of course, there's water velocity in the pipe, but reservoirs, our typical assumption is in a reservoir or a tank is that even if the water level's going down, it's going to be going down so slowly that we can neglect whatever velocity head there is at that location. And that turns out to be a really good assumption because velocity heads typically, even when the water's moving quite briskly, velocity head is a small fraction of how much energy is in any given spot. All right, so you can see here we're saying Z1, Z2 are both known from the problem statement. The pressure of each of those locations is 0 and the velocity is 0. There's no pump here, but we are going to be taking energy out through the turbine. So I've calculated the amount of head that's available for the turbine to extract. So what we're saying is that the energy between 1 and 2 is going into 2 spots. Very little of it as energy loss, and the majority of it is available to harvest as head that goes into the turbine. So then the power equation tells us how many watts are available if it's 100% efficiency, and then how many watts are available if it's 70% efficiency. And so in terms of kilowatts, what's that? About 3,700 kilowatts. During like peak air conditioning season, any given household may be drawing up to like 10 kilowatts. So this would only be good for a small neighborhood, the situation that's described here. And so typically at a real power facility, they'll have multiple turbines and quite a lot of flow because energy consumption is really high when people start flipping on the air conditioning. Any questions about this example? All right. Let's look at some key ideas of problems that you've got due in class next time. Because you've got an assignment due on Thursday, right? So that's our next class meeting. All right. Now, I always have mixed feelings assigning this problem because here we are in Chapter 7 talking about energy losses, and it's such a relief to finally be able to account for them. And then here in this problem, it says neglect head loss. And so it's like the whole reason we're in Chapter 7 is to not neglect head loss anymore. But I guess this is maybe more of a warm-up problem anyway. But what it wants to know is what's the flow rate through the pipe and how much pressure there is at B. And so chances are good that in all of the homework problems you solve for this assignment, you're going to need to refer to the energy equation. All right, so here's the energy equation. And if the outlet is here where it's going to a jet, remember that air surrounds the jet of water once it comes out of this nozzle. And the thing that we like about that is that when the air is surrounding it, it has 0 pressure. The water itself, since it's surrounded on all sides by atmospheric air, the water has 0 pressure. And so, it's always here going to be a matter of picking spots where you know location 1 and location 2. And location 1 is the reservoir surface. Location 2 will be the jet outlet. And you can use energy equation to find the velocity of the flow. So, of course, there's no pump, there's no turbine, there are no losses because it said to neglect head losses. So you're just going to be using essentially Bernoulli's equation since we've taken out the pump, turbine, and loss terms to find out the velocity at the outlet. And since you know the diameter of the outlet, you can find the flow rate from that through continuity. And then the pressure at B, you can also use the energy equation, and you actually have a choice of what's location 1 and what's location 2, because location 1 is at the surface of the tank, then that would make this location 2, and so we've got an elevation difference that's known. You know the velocity at B. Now let me give you a warning that the velocity at B is not the same as the jet velocity. Why do you suppose that is? Why are the two velocities different? Different diameters, right. Okay, so you're going to need to find out some velocity at B in order to find out how much energy is left and existing as pressure at B. So you could use the tank as your first location and B as the second, or you could say location B is 1 and then location 2 would be the outlet, because you know everything you need to know at both of those locations in order to do it. So, any questions about this one? All right. This problem's a little bit unusual because if you look in your book, it gives you mixed units. It's defining the problem in terms of cubic feet per second for the flow rate, and then all the other dimensioning is given in meters. Now, if you've already solved the problem and you assumed that it was a misprint and it must have been 3.5 cubic meters per second, that's fine. No need to make a change. But actually, it's not a misprint. They actually intend for you to do the conversion from cubic feet per second into cubic meters per second. Or shy of doing the conversion, at least looking on the slide here because I've done it for you. So you have 3.5 cubic feet per second is equal to 0.1 cubic meters per second. All right, so this is similar to the other problem that you've just done. You don't have any information that's defining energy loss in the system, so you're going to have to neglect it. You don't have a friction factor. They're not telling you energy losses. And so you know the flow rate. That's going to allow you to find the velocity at the nozzle. And they want to know what's the pressure head at 2. So if you know the velocity at the nozzle and the pressure of the air, and you've got the elevation, so you can know the total amount of energy that exists at the nozzle, and that same amount of energy has to exist at this location too. But they're trying to trick you, because remember, we usually say that we call 1 the upstream location and 2 is the downstream location. Well, here, even though there's no energy losses, it's still a good habit for you to remember that this location 2 is upstream and the nozzle location is downstream. So when it asks for pressure head, it doesn't mean find the pressure at 2. It's asking for pressure head, which is the pressure divided by the unit weight of the fluid. All right. So pressure head will have units of meters. Okay, so any questions before I move on to the third and final hint slide I'm going to give you for the assignment? All right. Now this one, you have to remember when we talked about cavitation and vapor pressure. Remember that when we discussed cavitation, what we said was that if the pressure of the liquid goes low enough that it equals vapor pressure, then the liquid will actually begin to boil, or it'll begin to go from the liquid phase to the vapor phase. And so what that means is that here in this venturi, where the throat contracts, the velocity is going to be higher. And since the velocity is higher, the pressure is going to be lower at that contracted throat. And if the water keeps going faster and faster through the throat, then that means that the pressure is going to have to continue to go lower and lower. And you'll get to a point where for 20 degrees Celsius water, you can look up in the back of the book what's the vapor pressure for that. You're going to get to the point where the velocity is eventually fast enough through that contracted throat that the pressure of the water is equal to the vapor pressure. And then that's when cavitation begins to occur. And so what it's asking you to find out is how quickly can the water go through this system, what flow rate Q can you have that just barely starts to cause cavitation at that contracted throat. So they call that incipient cavitation, when the cavitation just barely begins. And what it means is set the pressure at the throat equal to the vapor pressure of 20 degrees Celsius water. And so you're solving the energy equation. Again, this is another problem where head losses aren't defined, so you'll cancel that term out, cancel out the turbine term and the pump term, and pick a spot where you know a lot of information for location 1. And location 2 will be that contracted throat. And so the velocity is essentially what you're going to be solving for when you do that calculation. And then once you find the velocity, since you've got the diameter, you can find the flow rate as well. Yes? Excuse me? Oh, that's a great question. So he's asking, what about gauge pressure? And here, actually, you should be using absolute pressures. They give you in the problem statement that the atmospheric pressure of the air above the water is 100 kPa. And, of course, we know that in gauge pressure, atmospheric is considered 0. You know, that's our baseline for measurement. But here we have to use absolute pressures because when you look up the vapor pressure of liquids, those will be based on absolute pressures. They won't be on the gauge basis. So you should have both locations in terms of the absolute pressure, not the gauge. That's a great question. I'm glad you asked that. Other questions? All right, that's it for today. That assignment will be due in class on Thursday. Let me know if you've got questions, and I'll see you then.